Hello guys. So in this video we're going to start coding a data science project which is about breast cancer screening. So we'll try to analyze the data we gather from patient's history as well as the analysis of breast cancer, and we'll try to come up with different insights, and then we'll probably go into the modeling part and make modeling. So it's basically a overall end-to-end data science project. The data science part, the data engineering MLOps parts are not included, and then if we get time in next video, we'll try to make videos on how to deploy the applications or make, let's say, data apps using Streamlit or using some let's say data cloud, which is Snowflake or something, and we'll try to deploy those applications. Okay, live. So let's start. So what's this breast cancer screening is, if you see, normally breast cancer is the number one cancer that people today they're facing. So getting insights or generating some statement about it will be much more crucial, and it will help basically the doctors and the medical or healthcare providers to detect cancer early. And yeah, obviously it will help definitely in the healthcare domain to safeguard patients or human beings from early detection of cancer, and we can, probably help saving in couple of lives. Okay, so methods that includes in breast cancer screening is mammography, clinical exams, and self-examinations. And regular screening aids in identification of abnormality before symptoms appears. So benefits of this early checking includes early intervention and less, uh, costly investment in treatments. False positive and negatives are limitations. Obviously, screening programs contributes to public health and empower individuals in managing the health. Okay, so first what we'll have to do, we'll just import all the libraries. So as you know, will require NumPy for doing mathematical calculations. So I'm just typing all the codes here so you can follow along with the codes. So you can definitely type along with me. That will give you more confidence if you're new. And if you're not new, just download the notebook and follow along the video, or you can carry on, right? If you are not new. So then again, I need to import pandas as we are not dealing with big data, so we are not going for Spark configuration. We'll be working with the open source pandas library for manipulation of data. And then another important thing is matplotlib. Okay, for doing the plotting. And another thing will be required basically is Seaborn. Okay. So if it's already installed, you can type a tab to autocomplete it, and as everyone says, so I'll start with only these four modules, the beginning of the project, and later on, when required, we'll include the rest of the modules, right? That's how we start a project, right? So we need data, so let's give it a variable name as data. We have imported pandas as PD. So PD dot, if I do a tab, we'll see a read CSV. I know my files are in CSV. Okay, so a single tab will show all the files that included in the folder. Okay, so what we need a dataset folder, and then again within dataset, I need to go to archive, and then again in the archive I need to go to this data file. So this data file contains all the files that we required for displaying the data and for doing the initial set of investigation and analysis. Okay, now we'll set one. So pd dot set option. So if I do a, it will complete. Yeah. So this, what, why we are doing this, you will just get to know. And we'll need this display dot max column, and let me just keep it as 30 for the time being. And in this column only, now let's visualize what's data we have. So as you can see, it has a 33 columns and it is showing the top 5 rows. And you can see we have ID. This diagnosis is the main column that contains M and B. So that means your malignant and benign classification. Then you have these features called radius mean, texture mean. So you have three set of features. One set of is mean features, then one set of is your SE features, and one set of are worst features. So these three features are available, and based on these three features, we will try to do a classification. So we'll do the insight generation first, and then basic data analytics and data science project. Okay. Now let's move on. So as you can see in the profile, right, this unnamed 32. So I don't think this column contains anything, and it's probably some, miss data quality issue, something that's coming up. So first and foremost, we don't need this column. Okay. So what I'll do, I'll just first store all the columns inside this variable. So if I do a this method, right, dot columns is an attribute basically, and it will gives you all the column names. So now if I do a call, I'll see all the column names as an index. Okay. Or if I want, so I can also make it as a list for easy analysis. So you can see ID diagnosis radius mean, all these mean features up to this, and then we have the SE features up to this, and then we have the worst features up to this, and we have this unwanted unnamed 32. Okay, so what we are gonna do, so I'll just assign the data to data again, and I'll just drop. Okay, so what I'm going to drop this column which is termed as unnamed 32. So I'll just copy as it is and I'll paste here, and you have to provide the axis, otherwise the data frame is a 2D data frame, right? I mean it has two shapes, right? One x-axis, one y-axis. So the columns belongs to y-axis, right? So your axis belongs to 1. Okay, that means now the data we have is cleaner with this unnamed 32. So now if you see, we have 5 rows and 32 columns. Previously we had 5 rows and 33 columns. Okay, now let's move on quickly. Now what we want to do here, first of all, let's say I want my y, that means my level, as this diagnosis. Okay, so what I can do, data dot diagnosis, this column I can ensure it as y, and I want my list. Let's say I want one list, or if it's a keyhold, so I want this ID is basically identifier. So for analysis it will be of no use, and we already stored the diagnosis in y. So diagnosis, right? So I'll just going to drop this two from the list. Now I'll be requiring another x, right? So this x will be my data dot drop. I just want to drop the list, right? So list one, and as I have shared the formula, like the method, right? We need to specify which axis we want to drop. So we want to drop the columns, that means x-axis. Okay, now if I do a x dot head like data, So it is nothing but our feature. So you can see all the ID and diagnosis got removed, and unnamed 32 is getting removed from the data set. So I'll be having only this, okay, as my X variable, okay. And if I can see what's my data inside Y, I can see all the part of Y, right? So I can do a Y dot describe probably, and I can see the details. So I have 569 counts with two uniques, and benign is the most top. So it definitely falling in align with what we see normally in human prediction as well. Ki most people does not have cancer kind of ailment basically. So this is definitely going to be an unbalanced basic data set, right? So now let's move on, and let's move on to analysis. So first, that will be very much predictable. So after all this code, right, it's very much evident that first thing we need to do a count plot to see, okay, how many counts of benign we have and how many counts of malignant we have, right? So for this, we need a count plot. So your Seaborn provides very beautiful count plots. Okay, level, let's say, uh, I just for now let's keep it as count. Says we have already imported SNS. Okay, could not convert. There is a problem for converting string to float. Okay, so let's just first assign. So what it was doing, right? Why it was failing basically. So let me tell you the reason. So these things you will get to know once you will do actual coding, and unless and until it's very tough for you to crack a job. Seaborn, right? So if you go to this Seaborn count plot, and you see x and y, okay, so when I am typing y, so it is taking the y, and it is not taking the x variable, okay. So it has a data, I mean arguments x, y, hue, order, you order, color, palettes, saturations, axis, and some arguments that we can pass as a white, okay. So that's why like it is giving us error. Okay, so now when we are using this x equals to my y, then it will not give you the error. Okay, now if you just copy the same thing and you just change the x to y, and you will see that it is not throwing any error, right? So you have to mention, otherwise what is happening ki it was fetching it as data. Okay, that means, so when it is taking it as data, you are getting this error. Okay. So the default one, it will take as data. So be aware of this. So now we have this count plot, right? So we can see there is approximately more than 350 values of benign cases we have, 357 to be specific, and the rest 210 or 12, right? 212 cases of malignant cases we are having. Okay, now what plot can we do next, right? For getting more insights. Let's say I want this as percentage, right? So now let me just, you know, as you can see, this plot is good, but it's not giving me the actual uh, domination of each and every uh, count of malignant and benign. So in these cases, a pie plot represents the situation much more better, and that's what we are going to do in the next couple of line of codes. So let's say I want to do a pie plot using, now I'm going to use a plotly plot here. Okay, So let's px dot pi, and y will be my value that I want to do. And in values, is my spelling correct? Yeah, values, I want this y dot value count. So is a function that you can use that will give you the counts. Okay, and dot values. So I'm taking this one, and my names will be the same. Okay, why it is not showing up px? Okay, probably we haven't imported plotly, right? Yep. So we're going to import plotly here. So what we need import plotly dot express as px. So now we have imported plotly, and now you can see the names will be again y dot value count. It's some method, and again we need index of those. Okay, so this, so what it will do, it will create a figure object as you can see here. And now once the figure object is created, we can do manipulation with that object, right? So let's say I want to add, so it's the grammar of visualization basically. So figure, so why it is not coming? Because figure is not recognized, right? So if I just run it, right, this figure object, let wait for it to run. So now I have this figure object with me. Now let's say I'm going to run figure dot, I'm just going to update the traces. Okay, you can see a lot of options are there, right? So update trace, right? I'm going to update the trace, and if it is hovering over, I just want to show the info. Okay, so what will be my hover info will be level plus percent that I want to show, and in text I want to only show the values. Okay, and then finally I want to plot the figure object, that means fig dot show. Okay, so you can see now if I hover over, I can see the values and labels. That's what we have written here. And in text values, we only want the values. In text, the information, we only want the values. And this is the indexes. Okay, so that means for benign, we have 357 cases, and for malignant, we have 212 cases. Okay, so we are good now. Now let's build some box plot visualizations, because as you can see, if I do a x dot describe here, you'll get a lot of continuous values we have. That means this all these continuous values, right? These must be must have these five statistical points that we can analyze, and we can also do a description, or basically a division between malignant and benign, and if we try to see if there is any difference between the features and the predictions. So let's it's also simple, right? Let's start. So again, you need another figure object where you need px.box for a box plot, and there you need to send the data. So I'm just sending the previous old data. That means the data where we only have dropped this thing, right? This unnamed 32. So it will have 32 columns and 569 rows, right? This data, and what it requires basically, It needs a column in Y. So let's say I want this radius mean, and I want this color. So I can also discriminate based on color, and that I'm doing with the diagnosis, right? And then what I will do, I am going to plot this. So fig dot show. So as you can see, I can see all the statistics here. So you can see a clear distinguish. We can clearly distinguish a malignant case and a benign case based on the median values. As you can see, the median for malignant is much more higher in case of this radius mean feature, which is much more lower in case of this benign feature, right? So for malignant, it is 17.3275, and for benign the medium is 12.2, and you can also see some outliers. Okay, so these extra points are outliers that we are mentioning. That's a default plotting criteria basically for uh, this box plot. So if let's say I don't want outliers, I am going to set a all feature. Okay, okay, it must probably it has to be before this color. Okay, second. So as you can see, if we change the method of points, right? So we can see all the points here and the distribution. Okay, so if you see that there are some patients or some cases where we have the radius mean for malignant basically is much higher, but in case of benign, right? So that means it must follows a uniform shape. So the radius follows a very strict, it's probably between the uh, what it's your 75 plus 1.5 IQR to 25 minus 1.5 IQR. So this range, it is strictly following where we can see a good amount of distribution, right? The spread is very much well in case of malignant. So, yep, that we can visualize using this box plot. So we can just copy paste the same, right? Plot we want, and we can change it to, we have the second one as texture mean, right? So we can very visualize that as well, and we can also verify here that for benign, right, it's mostly uniform, but here also we have a lot of outliers outside here, right? And in this case, the texture mean the malignants are much more conserved basically, and very few outliers we can see. So if I do a outliers, right? So it's also following a statistical equation for giving you the points. So you can see uh, here we in case of benign we have much more frequent points in case of outliers, and in case of malignant the numbers are quite fewer than the benign. Okay, now the same thing I'll do for another feature, and I'll stop here. So let's take one worst feature, and let's take radius worst, and let's see if there is anything we can discover from this. Okay, so as you can see, same thing. So everywhere, right? The difference between malignant and benign is pretty much determined. So here also, if you see the median value is 21.5 approximately for malignant, and for benign it's 17.4. So quite pretty evident, the 4 unit difference. The same thing is also here for radius worst, it is having 20.6, and for median for benign it's 13.6. So a 6 unit difference, right, between these two. So these are very good predictor and features basically that we can see for detecting whether your breast basically is having cancer or not. So whether your cells or breast cells are having cancerous or not based on these features, right? So these are good insights that we can see. And again, if we want to see the distributions of the data, I'll just make it to all. And you can see again, it's mostly conserved in case of benign, as you know, regular cells or regular human being or regular things will follow a definite a bound shape, basically of the radius or whatever diameters or things will be limited, and those things that are disease prone, or those cells those are disease prone, basically malignant here, will have abnormalities in, right? That's how clinical trial happens, or we diagnose features or basically diseases using some scans and blood tests, right? So now let's move on from the box plot and let's contribute our analysis in the next set of things that will these are basically your univariant analysis, right? So all these things are univariant analysis. Now we'll go to some bivariant analysis here. Okay, so we see that the power of C bond, right? So we have already done the count plot using C bond, right? So let me just connect to internet. Why it's not connecting? Okay, now we are going to do a joint grid plot, or basically pair plot in Seaborn. So let's just do a SNS dot joint grid I want. So in joint grid, I have my data, and then I need two things, X and Y. So what will be my X? What will be my Y? So in X, let's say I want my data dot uh, concavity worst I'm going to take here, and in Y I want my data, and here also I'm typing in a different manner. I need my concave worst uh, points, basically. So the features are like this, and once this joint grid is done, right? So SNS dot joint grid, you can see. So nothing is coming out here, right? It's only the points and the labels, basically. So what you have to do first, you have to initiate this plot, and you have to store the figure, basically this figure, as a variable. So let's say G is the variable, and then you have to use a function called plot join for plotting. Okay, why it's not coming? So I now want my joint to be plotted, and I want SNS dot scatter. I want this scatter plot, and I want my S to be 100, and you have to give alpha. So these are some visualization parameters that you have to provide, right? So my alpha, let's say I'm setting at zero point 0.7. Okay, so now you can see the data. So now previously the first line, what it did, it plot the grid, right, between these two variable. Then you have to plot the data inside. So now I'm plotting the scatter data of these two, right? Concavity worst and concave point worst. So what we can understand from this, right, if you see closely, that the data point between concavity worst and concave point worst are mostly linear, right? So if you see, if you make a regression plot and you find what's the R value, I mean, coefficient of relay, what linear coefficient using Spearman or Pearson, you will find it's more than zero point 0.8 or zero point 0.9. Okay, so that one thing we can understand. Now next thing what we also do, that we can plot the distributions of the individual univariant values or features of this two. axes basically. That means my concavity worst in this position and my concave point worst in this position. So in the next line, let's do that. And again, let's recreate our plot. It's G dot. Now I also want my G to be plotting the marginal values. Okay, so you can see this plot marginals, and inside I want, let's say, SNS dot hist plot I want. That means I want the histograms and I want the distribution to be true. And now if I do that, I can see the same plot with much more insights. So now I can see there is a left spike. That means it's right skewed. This concavity worst is having a right skew. That means most of its values are towards lower range, right? From zero point 0 to zero point 4. Within this region, we have much more values, and it's also, let's say I'm just make the alpha little bit less for understanding. So you can see here, you can see, so these are the very faded points, and these are the points where we have much more concentration, so that you can understand. And the same thing for concave point worst, you can see here, but it's completely a different distribution. So it has a more value towards the lefter one, and it has long tail towards the left and more value towards the righter one. That peak is in the righter one, so in this position, right? So that's how you can identify. So most of the values are ranging from for concave point worst is from zero point 0 to 0.50 15, and for this case it is ranging from zero point 0 to zero point 4, right? So that's how you plot a joint plot and you visualize the things, right? Now next thing that we can do for understanding much more better the relationship between these two basically points, why we are going to do the same kind of plot, okay, but we'll just change these two lines. So what we'll do, we'll just do a simple plot, okay, and in the plot we'll be mentioning that whatever plots we'll be requiring. I want a regression plot to understand the regression, and let's say I want a box plot to understand the three quartile or outliers. So as you can see, this concavity works, right? It has a lot of outliers based on the statistical approach we follow of IQR, and this concave worst point, right? It has a very less or no number of basically outliers. So if you just given these two features, right, for prediction of diagnosis of this malignant or benign, right? Now there will be an interesting question, ki which parameter are you going to use? So if you look closely, these two, I have outliers here, right? I don't have any outliers. So these outliers might be a feature. So let's say might be all these points will be belonging to malignant tumors. So you can see this regression, right? This regression line, it's a very strong coefficient, right? Between these two parameters. So what we can do, we can ignore this parameter. That means your concavity worst, and we can take this concave point worst for our prediction. So that's how you reduce the number of parameters. Okay. Now what I want to visualize the same plot, let's say in a different manner for far better understanding. So see, we have started with this plot, now we have come up to this plot. Now in the next plot, we'll include much more variety. So you and I am typing it in a different fashion. So first we have used dot notation, then we have used this bracket notation. Now we are simply, as we have mentioned the data, we have simply going to mention the name of the column diagnosis, so that it will automatically understand ki use the diagnosis column for you know discretizing the data points, the colors of the data points basically. And I want, again, I don't want a regression plot now because that regression part is done. So I want again a simple scatter plot, and for plotting the univariate values I want a histogram. Okay, so now here you can clearly see, okay, this benigns, right? Most of the values are benigns, and you can see this benigns for this concavity worst are falling under point 0.2 to point 0.4. And as we have mentioned, right, ki this cannot be outliers, so this might be data points that are causing malignant a tumor. So that's how doctor will suspect, okay, if it is in this range, so this is outlier, treat it at most emergency. And you can see these are belonging to malignant feature. Okay, so that's how we do the classification, or we do the segregation before machine learning. And you can build your intuition or your hypothesis testing for further analysis. So this is how you do the classification basically. So now with the hue, distinguishing hue, right? So here also you can see a clear distinguishing between the benign and malignant. So malignant, of these two features, right? Of these two features, malignant has a separate set. So you can clearly draw a simple line from, I think, this 0.15, right? Yeah, from here you can clearly draw a simple line, and you can distinguish, right, whether it is which data points will be malignant and which data points are benign. Okay, so that's how you will understand the joint distributions. Now next, move on, we'll do the same kind of analysis with another set of parameters. Let's say I'm trying to now use radius mean again. So radius mean, as you know, that will be our bread and butter for this project. So this radius mean, and let's say I want area mean, and same thing, I want this color segregation, and I want this color scatter and histogram plot. So normally for any, let's say it's a cell, right? We are diagnosing the radius and perimeters and area. So I don't think whether the measurements are exactly a circular or not, but you can think it's mostly a circular thing. Then your R, and there is a relationship between radius and area, right? So you can simply develop an intuition like that, and that means your area will be some pi r square and your radius is r. So if you go and relationship between radius and area, and if you go for images, you will find some set of curves. So you can see this is a curve that shows the relationship between area and radius. Okay, and if you see our plot here, it's mostly similar kind of plot. That means it is following a perfect example of area and radius and derivation, right? So you can deduce any one of these features. So we'll be deducing the area mean for our prediction stuff, and we'll be concluding that, okay, let's move on with radius, and we don't need area because they are deriving from some formula basically. Okay, and that's how your parabola shape looks like. Okay, x equals to y square, right? And here also you can clearly distinguish between benign and malignant. Now let's, you can also do a same kind of approach for, let's say, perimeter we want to see, right? So we have this perimeter mean, right? So we can perimeter mean here, and let's say, what kind of plot, I don't want to plot the same kind of thing here. So I'm using, I don't want to use a grid as well. We also have a joint plot option. So I'm going to use that joint plot that provided by C1. And in that plot, I'm passing my data, I'm passing my X, I'm passing my Y, I'm passing my hue. The only thing I need to pass is what kind of plot it will generate, right? So let's say I want a histogram kind of thing. So I'll pass this hist as command, and you can see it will generate me a plot exactly same like this, and we can verify it's very linear, right? So again, our my perimeter's formula for a spherical thing is 2 pi r, right? So my perimeter will be proportional to my radius thing. So that assumption also you can verify your hypothesis from this plot, and you can get the regression coefficients and all for your further analysis. Now, next what we can do, we can show some kind of regression stuff as well as here, right? So just copy the same plot, and this I'll change it to reg for regression. And if I do a plot dot show, okay, what we can also do as part of visualization, I'll just plot dot figure for changing the shape. And here I have to choose a fixed size, and let's choose it between 12 comma 8, and then I'll have to do a show for showing the plot. Okay, so as you can see that if we are using this hue parameter, then this regression plot we cannot use. So for time being, let's just remove this u, or because definitely, right, if you're doing a regression, then you cannot do separate regression for separate classes, right? So the data points has to be similar, same. So now you can see a regression line, and as well as the distributions of each and every uh, parameters basically here, right? So what we are understanding the same, right? Keyword perimeter is proportional to your radius, right? Now next what we can do, we can again move to joint grid, and we can prove some points regarding, let's say, previously we started with concavity worst and concave point worst, right? So let's do that again. Let's just copy, and again joint plot I don't want, I want a joint grid. And in the data I want an X as to be my concavity mean, and in Y I want a concave point worst, right? These two things that was our point of interest. And now I don't want any regression, I just want to see, visualize this two individually how it looks like. And this diagnosis will be my segregation mark, because that's our point of interest. And again, for grid, right, you have to make it a variable, and then g dot sns plot, right? Sorry, g dot plot. Basically in the plot you want a scattering thing, so sns dot scatter plot. And again I want this time the distribution plot, so my KD plots will be there. So as you can see, for benign, I have a clear spike here. For malignant, I have more spread here in case of concavity mean. So that's why we choose these two features previously as well, right? Again, here you can see for benign a clear spike, that means concentrated data points here. And for malignant, we have much larger data points and much more basically spread, right? So that's how we can definitely identify with these features, okay, which one are going to be benign, which one are going to be malignant, right? So we'll take a quick break here, and we'll join the further analysis uh, post break. So you can see you have done a lot of things till now. So we'll be doing much more basically analysis of this data set after one short break. So now as we move on with our analysis, so let's do a pair grid plot distribution between radius worst, perimeter worst, and area worst. Okay, and we'll try to find if there is any similarities or is there any association between these three. So for doing that, what we need, I'll be doing that in Seaborn. So let's just set the style and let's for now we'll set it to white and let's see if there is any opportunity available, okay, apart from white. So set style, okay, so different opportunities are there, right? So let's use this dark grid for now and I mean just fancier graphics we'll get. Now let's create the data frame. I'll be using a lock method here. I already hope that what lock and ilog does. If not, please comment. I'll let you know in a separate short video what is the use of lock, or you can simply, Google it. So we'll have a radius mean, sorry, radius worst, and next one is my perimeter worst, and the next one is area. Okay, so I have all my features intact and I have the data frame created. I have set the style. Now I need the grammar. Based on the grammar of visualization, what I need pair grids, right? So I'll do a pair grid quickly here and I'll have my df, and in apart from df I'll need, should I need to share it with diagonal, false. Now as you can see, if I just plot, okay, this g along, it is nothing but a variable, right? So you can see, I can see the plot how it will look like, but there is no concrete things, right? Okay, no data is coming on. Why it's happening? Okay, so because here what you have to do, you have to make, so now what this three code does, as you can see, so sns dot set this dark grid will make this grid as dark. Okay, now this df is for your data frame, that I need relationship or distribution between these three, and then you want a pair grid. Okay, so that's why a pairing structure comes, right? Now the next thing, what it needs to print here. So understand this codes, right? What the code is doing rather than just copying and pasting. Okay, now I want this g, which is my plot variable or plot function. I want a lower mapping, so map to lower. Okay, and in map lower I want sns dot density plot. I want, so I'll just do a kd plot, and let's say cmap equals to, I want blues, so the color what I want is blue. Okay, sorry. Okay, now I think I have misspelled here. Okay, so what this map lower will do, you will get to see in a moment. So you can see this lowers, it is creating this density plot. Okay, basically your contour plot. Now in same logic, you need to fill all the upper diagonals, right? So this pair grid is creating the grid. It's a 3 by 3, 9 plots. Okay, now map dot lower, this function will fill all the visualizations for your lower part. Okay, now you need this upper and this diagonal. Okay, so I need one upper, right? And let's say here in upper I want scatter plots. So plt dot scatter. Okay, so you'll see all my lower diagonals and all my upper diagonals are filled. Now I want in a same manner I want my diagonals to be filled. So map dot diagonals, right? So if I do a D, I think it should automatically populate here. Yep. And here what I want, again I want a density plot. Okay, sns.kd. Okay, here let's use some another argument. And now you will see I'll have a density plot. So diagonal plot means plot with itself, right? So you'll see the density means as an histogram. So as you can see now all my nine plots are filled. Okay, so I can see there is a close relationship with radius, perimeter and area. So all these three plots, right, is showing the relationship between radius, perimeter and area. Now let's move on to correlation plot. So it's the most easier plot to figure out the correlations between all the features and eliminate. So what I'll do first, I'll need one axis and a figure. For that I have these two variables, so for which I need this plot, and I need to use this subplot function, and I need to use fixed size argument that I have to provide. And let's say I want this because it will be a big amount, I mean big size of plot, right? Because as you know that we have a good amount of features. So these two things will hold the subplots. Next, what I want a heat map, nothing else. That's what a correlation map dictates. So I have my X and this CORR, right? This CORR will give you the correlation plots. And then what I need whether I need annotations or not. So I need annotations, so I'll make it as true. Okay, and the next one is what will be the line width. So these things, this thing, I mean formatting things that you have to make sure every time you are presenting your work or you are presenting a visualizations, you have to make sure to use this additional features. So let's say in here I'm using this line width as zero point 0.5, and let's say I'm using the formatter, right? So what will be my showcasing formatter? I'm using it as point up to 1 in float, and then I'm providing my axis. Okay, so you'll see a good amount, I mean good looking plot needs to come. Why it is not? So unexpected keyword is fixed size. Okay, so okay, I misspelled. Okay, subplots is the function name. Typos, I think everyone faces this typos while they do. So now you'll see a good heat plot will generate with the function of heat map. And yeah, and the lighters are more towards to one, so I can see radius mean with this, what is this, perimeter worst has a complete one regression coefficient. Then perimeter mean is also with perimeter worst has a coefficient of 1. And I can also, this is diagonally I can verify. And here also if I see perimeter worst has a complete correlation shape with let's say this is perimeter mean, this is area mean, this is again perimeter worst, so same, this is here radius worst, and also area wars. Okay, so these are correlated features. By seeing this plot, we can definitely eliminate some of those or mostly. Okay, and we can figure out, right? We have this L1 and L2 regularizer that does the same thing. Okay, if you have a huge amount of feature for doing selection of features, you are using L1, and to keep all the features, but with marginal coefficients, you use L2, right? So that thing we normally used to do, right? And the next task will be correlation plots of the mean features. Okay, so for this, what we need all the mean features. Okay, so if you remember, we have this call thing, right? Which is holding all the column names as an index. So how we can get the details of feature means? So this all features are mean features, right? And we want to see the relationship or correlationship between these mean features. We don't need this SE and worst, okay, for this analysis. So feature mean, let's quickly go and set this. Okay, and I want this call from 1 to 11. Is it that I want? Okay, yep. Feature mean I got. Now, but if you see, it will be in index, right? So you make to change it to list. So I'll need it to feature mean. I need to convert it to list. So to list is another method that I'm going to use. Okay. So for finding correlation, define one variable. Let's say that's correlation, and in data I'm using this feature mean, and then to list function for making it as list, and then I'm using from I don't I'm do, not going to use this diagnosis, right? So I have included diagnosis wrongfully here. I don't want to use this diagnosis because it's not continuous variable, right? It's the target variable basically, and correlation. So it will give me the correlation function or correlation matrix, so I can verify it, right? So you can verify the correlation matrix here for all the mean features. Now what we want a figure. Okay, so plt dot figure with along with fixed size, right? So that's I'm missing something, right? A fixed size. So that will give us the size for plotting. So let's keep it as 14 12. You can okay, let's keep it as 14 14. And again this sns dot heat map I'll be requiring. So here I'll be passing this code only. Okay, and let's see how the plot comes. So as you can see, the plot we are seeing, but we are unable to, seeing it in a very good manner, basically, if I can say. Like you cannot quickly come to an conclusion by seeing this. So we'll make this plot a little bit nicer so that, when we are presenting our work, it will be much more relatable to whatever we are speaking. So let's use a function or argument called c bar. Let's make it true, and then we'll see what this does. So this is basically your color bar. Okay, now let's make it a, do you want it to be a square, right? So it's basically a matrix. So matrix normally it is a square matrix, not a rectangular one. So I want to fade it as a, or I want to share it as a square one. Okay, so we'll just make it a square. So you'll see now the shape is much more, understandable, and we can find out some meanings here. Likewise, we can see that radius mean has a strong relationship with perimeter mean and area mean, like previous, and it also has a good amount of point 0.8, right, with concave point mean as well as uh, your compactness mean, right? all these have more than zero point 0.5 your correlation ID basically. Okay, so further we can make improvements on the same code. Let's say I want annotation. So what I'll do, I'll make the note as true. So you'll see all the annotations. That means all the points are coming up. So you'll see that perimeter mean has a good stronghold 0.85 with concave point mean. That's the points are coming. Now, next thing what we're gonna do, I'll be using this labels as feature mean and ytig is also my feature mean, right? So I'll just copy this. Sorry, Control V. Okay, Control C and Control V, feature mean and ytig. Okay, comma is missing, and we can see now a much more good labeling here, and we can definitely change the color. So I think color is not CMap. I'll have to use. Yep. So let's make this a school worm, and we'll see a good graphical representation of the mean features correlation. Okay. Now, what I am trying to do in the next plot, so first we have come up with all this jibber jabber, right? It's a lot of features. Then we have only seen the correlation between the mean features. So the same thing you can do for your SE features and worst features. And I'm not going to do here. And the next thing that I'm going to do here is I'll do a correlation with a threshold. Okay. So I already have this CORR, right? That means my correlation matrix available with me. So let's just define one threshold, and I want that to be a 7.5, and I want a filter included. So in PABS as an absolute method, my correlation matrix, and I want the threshold to be applied on radius mean. Okay, and let's give it greater than threshold. Okay, so this is my filter data. Okay, this is now my correlation feature will be my correlation matrix. Okay, then columns, and in columns I'll pass this filter, and then I'll just make it as a list. Okay, and once this is done, I'll not do a heat map this time. I'll do a cluster mapping. Okay, and I have my data available with me, and with the data I have this correlation features I'm going to use, and then I'm going to use the correlation function, and I'm doing the annotation equals to true, and that's it. And let's plot it. So as you can see, now I have all the features. So it includes only the features that has uh, correlation of greater than equals to 0.75, right? Greater than 0.75, along with respect to this radius mean, right? So now we have started with correlation of 30 individuals or 30 features. We dig down to a particular point where I can conclude, okay, I can use only one feature, that is radius mean, instead of all these four features. So that's how you use a visualization in your data science project to reduce your workload. Okay, so again we also have another data, that's our patient data. So we'll let's say come later on, we'll do the analysis of our patient data. So now we have done all the detection of methods, right? I mean, we have a very good amount of analysis performed here. So let's do basically a machine learning model. Let's build a machine learning model. So for that, I need my training data, then I need my testing data, then I need my training data again, and again I need my testing data. Okay, and for that I need one function from sklearn, that will be train test split. So I'll be importing couple of libraries here now, okay, for doing machine learning. So let's say from sklearn it should come, yep, dot model selection, import, what I'm going to import, train test split. Okay, the next import will be from sklearn dot neighbors. I want to, let's say, import k neighbors classifier. That's the one thing I want. Next I want neighborhood component analysis. These two thing I want. Okay, again from sklearn pre-processing, I want to import standard scalar, and next again from sklearn I want from model selection. So we already have model selection top there, right? So apart from test and split, I want this grid search to be enabled. For matrices, let's say from sklearn dot matrix. I think I have two versions of sklearn import. I want to import accuracy score. Okay, why it is not? Yeah, it came. And confusion matrix. So this couple of things I want, and once it is there, I'll again go to the notebook, right? So in the notebook now I'll bring some machine learning model, which will be much easier for your understanding. So how to do the basic level of model building and all that. That's what we are going to do here. So I'm using here the train test plate. You have X, you have Y, you have test size. So let's give a test size of 30% for now, and random state for getting same result. I'm using 23 as a seed. So now you can check all the shapes. Okay, so I'm dot shape in everyone. Okay, shape. I think it's only attribute. So we'll just use a dot notation and paste it. Dot control V, dot control V. So you can see the shapes, okay, and you can also use the size function to get the dimensions of this train and test data set. So let's just, as we have too many features, right? So first thing, and mostly our scalar are continuous features. So first thing will be what we are doing, scaling, right? So in scalar, let's prioritize the standard scalar that we just imported from sklearn. Now let's build xtrain that will be my scalar dot fit transform, and I'm sending my xtrain here, train. Okay, and in my test, what I'm again doing a scalar dot transform only here. Okay, and I'm sending test, and that's it. So after this, what we have to do, let's say uh, we have to perform the machine learning model basically here, right? So how we are gonna do this? So yeah, now what we are going to do, we'll just create one, let's say, data frame out of it, of whatever we have this test and train, and then we'll train on some data and we'll validate and we'll perform. Okay, so let's just create one data frame. So pd dot data frame, and we'll pass this matrix, which is my xtrain, and column names will be the previous columns, and we'll see the data after the scaling process, what it looks like. So as you can see, the values now after doing the transformation or standardization, how it looks like. Okay, so is it correct? Xtrain. Okay, so what we have done something wrong. We have to send this one as uh, train, because xtrain is not scaled matrix basically. So yep, this one is a scaled matrix, and from this we have built this data frame basically. And our xtrain will also have one diagnosis column, and that will be my y train, right? So now if I do a head function, I'll be able to see my labeling as well. So as you can see, now the labels are included. Okay, so the first thing that we'll try here, let's do some dimension reduction first. Okay, and we'll do one machine learning model and we'll stop. So for doing, let's say, dimension reduction, right? So let's do a simple PCA method for this project. Okay, so for doing PCA, you need to import PCA, right? So my PCA will be PCA that I need to import, and number of components. Okay, so let's just import PCA. Let's say I want two, only two components. Okay, okay, sorry. It will be a decomposition method, right? And not a neighborhood method. So yeah, from decomposition we are importing this PCA, right? And next what we are going to do, you are going to do a PCA analysis on this data set and we'll try to figure out the malignant and benign using PCA method. Okay, will that be fine, right? Okay. Now once we have our PCA variable, basically you can see what this PCA is. It's nothing but a decomposition method that will decompose basically the whole data frame, and it will create only two components, keeping aside all its spread, all its variability basically. Okay, so uh, this PCA dot fit method, right, will fit this PCA variable on our data. So let's say mm, we have this data as X train, right? So this X train, and if I do this PCA dot transform of this X train, and let's say X reduced, so this reduction is basically holding this. So let's say my PCA data is now a PD dot, let's say a data frame. Now I am passing X reduction. So this is my basically what after applying this PCA method, whatever result we are getting, that means we have only used two components, right? So we'll get P1 and P2, these two components. So that will be stored here. And let's say for building one data frame, we need columns, right? So in columns, let's say passing a list of P1 and let's say P2, and that will be my PCA data. And let's say PCA data, I'm going to build again diagnosis, right? Diagnosis, and let's say that will be Y. So once we have that, we can verify our PCA data, that how this data looks like. So you can see the data we have with 30 or 31 odd columns now reduced to only two columns, that keeps including all the features, and we have our diagnosis columns along with us, right? And now if I just do a scatter plot of this decomposition, right? So let's do a scatter plot here, and in the scatter plot let's pass x as p1, y as p2, and let's specify how want to segregate the data. I want this data to be segregated based on target. Target is nothing but my diagnosis, and my data is my PCA data, right? And let's say a single title to the plot, PCA distribution of data. So you can see it has segregated the data, the malignant and benign data. Now, based on these two data, I mean, based on these two segregation, right, you have to apply the classification. the classification model. Uh, let's say you are going to use some KNN model or some other model, right? For that, you have to use this one. Okay. So the Canaan part and all the other part I'm not going to do in this video. So we'll be coming up with another video where we'll be deep dive from this analysis, where we'll have much more theoretical talks as well as hands-on explanation to know or to understand all of this. Or if you already know, it's very well for that. But if you want to know or learn more about data science, keep subscribe to this channel and watch out for more videos. Thanks.